Something is out there. Beyond Neptune, beyond the last planet on any map we've drawn, past the frozen edge of what telescopes have ever confirmed, a world nearly 10 times Earth's mass, orbiting so far out that one full circuit around the Sun would outlast the entirety of recorded civilization. No one has ever laid eyes on it, but twice now, infrared telescopes have caught a faint glow sitting right where it should be, and both times, the data has stubbornly refused to add up to a clean answer. On top of that, 6 distant frozen planets all point toward the same invisible force, and our entire solar system is tilted by 6 degrees in a way nobody could explain. If you enjoy this type of content, consider liking and subscribing to the channel. It truly helps me. Now get comfortable, let's begin. You already know the 8 planets, Mercury through Neptune, 8 worlds circling one star, laid out in careful order like chapters in a book everyone assumes is finished. That's the picture most of us carry around. A tidy, complete solar system, mapped and measured. But that picture ends far too early. The solar system doesn't stop at Neptune. It keeps going for billions of miles more into territory that most people never think about at all. Beyond Neptune lies the Kuiper Belt, a vast ring of frozen debris left over from the solar system's formation. Icy fragments, dwarf planets, and ancient rubble drifting in slow, patient orbits. Beyond that lies something even stranger. The Oort cloud, an enormous spherical shell of icy material that wraps around the entire solar system like a shell around a seed. These regions are so far from the Sun that its light arrives diminished almost to nothing, a bright point in an otherwise black sky rather than the warm disk we know from Earth. Out there is no warmth reaching the ground, no atmosphere to scatter light into blue skies, nothing but cold, dark, and silence stretching for billions of miles in every direction. This is the story of what's hiding in that silence. Not a signal beamed deliberately across space, not something torn from science fiction, but something quieter and in some ways more unsettling. Bent orbits, faint thermal glows, and gravitational patterns that refuse to behave the way empty space is supposed to behave. A trail of clues so consistent, so mathematically precise, that the scientist who found it couldn't simply let it go. And a search so difficult that 10 years of dedicated effort have deepened the mystery far more than they've resolved it. To understand why, it helps to actually stand at the edge of what we're talking about, at least in imagination. The trail begins at the outer boundary of the Kuiper Belt, in a region astronomers call the extreme outer solar system. To get a sense of the distance involved, a commercial airplane flying there from Earth would take roughly 5 million years to arrive. From that vantage point, the Sun shrinks down to a single sharp point of light, still brighter than the surrounding stars, but nothing like the blazing disk that warms our planet. There is no glow reaching any surface out there, just absolute cold, absolute dark, and a silence so complete it's difficult to picture. Objects drifting through this region move at a pace that makes glaciers look impatient. An orbit around the Sun out here isn't measured in years or even centuries. It takes thousands of years to complete a single circuit. These are some of the oldest, most frozen bodies in the solar system, tracing paths so slow that studying their motion requires patience measured not in days or months of observation, but in entire human lifetimes strung together. And yet, despite that stillness, these objects are not silent. Their orbits, slow as they are, carry information about everything that has ever influenced them. When astronomers first began charting the orbits of the most distant of these bodies, the expectation was simple: disorder. After billions of years of gravitational chaos, with no single dominant force shaping this remote region, the natural result should have been random orientations, objects tilted every which way, pointing toward no particular pattern at all. That is, after all, what chaos produces. That expectation turned out to be wrong. What the data revealed instead was alignment. The most distant objects astronomers could track shared strikingly similar orbital orientations. They clustered together in space, tilted at nearly the same angle, sweeping through the same general region of the sky as though something had arranged them on purpose. Run the numbers, and the odds of 6 independent objects falling into that kind of configuration purely by chance come out to less than 1 in 14,000. Picture dropping 6 separate sticks onto the ground from different heights at different moments with no coordination between them, and watching every single one land pointing in exactly the same direction. Nobody would call that a coincidence. Everybody would start looking for whatever was quietly pointing them. Something was doing exactly that. Something with enough gravitational reach to organize scattered, frozen worlds across billions of miles of empty space into a shared formation, unseen, unconfirmed, but undeniably present in the mathematics governing their motion. Researchers didn't stop at noticing the pattern. They built models to explain it, running simulations again and again, asking what kind of object could produce this specific effect and continue producing it consistently across billions of years of solar system history. The answer that kept emerging, no matter how the simulations were adjusted, was a planet. Not a small one either, something carrying roughly 10 times the mass of Earth, an ice giant in the same broad category as Uranus and Neptune, sitting in a distant orbit that no telescope had ever been pointed toward with any serious, sustained intent. It's worth pausing on what that comparison actually means. Uranus alone spans roughly 4 times the diameter of Earth. Neptune radiates more energy back out into space than it ever receives from the Sun. These aren't minor, forgettable worlds. They're massive, complex, active planetary bodies in their own right, each one a small universe of weather, chemistry, and internal heat. The models being run weren't describing some faint asteroid or icy pebble. They were describing something on that same scale, sitting in a place so remote that a beam of light leaving the Sun right now would take more than 6 hours just to arrive there. The mathematics didn't stop at estimating mass either. The simulations produced an orbital shape, a long, extraordinarily stretched ellipse, so vast that completing a single lap around the Sun would take somewhere between 10,000 and 20,000 Earth years. They produced an estimated distance of roughly 46.5 billion miles from the Sun, and they produced a general direction to look, somewhere on the far side of the solar system from the clustered objects that had first revealed the pattern, in a wide, unexplored stretch of sky that had never been the deliberate target of any dedicated search. A name followed naturally from there, Planet 9. Naming the hypothesis, though, was the easy part. Actually testing it was another matter entirely. Neptune itself sits about 2.8 billion miles from the Sun, and even at that distance it's already faint enough that you need real optical assistance just to make it out as a pale blue dot in the sky. Planet 9, if it exists, would sit more than 16 times farther away than that. At that kind of distance, any reflected sunlight bouncing off its surface would be diluted almost into non-existence, buried in the crowded, star-filled background of that region of sky, effectively invisible to the kind of search that found every other planet we know. But the orbital clustering wasn't the only thread pulling in this direction. As researchers kept digging through the data, they uncovered a second anomaly, older, quieter, and sitting in plain view for decades without ever receiving a satisfying explanation. It turned out the solar system itself wasn't sitting level at all. Every planet orbits the Sun within a shared flat plane, one that inherited its orientation from the spinning cloud of gas and dust the entire solar system originally formed from. According to standard physics, that plane should line up almost perfectly with the Sun's own equatorial belt. Instead, the whole orbital plane of the planet sits about 6 degrees off from where it's supposed to be, a tilt shared collectively by 8 substantial worlds, all leaning the same direction, as if something with a very long reach had been quietly tugging on the entire system for a very long time. No standard model of solar system formation produces a tilt like that on its own. For decades, it simply sat there in the data, a known oddity with no clean explanation, waiting for someone to connect it to something else. When researchers finally ran the Planet 9 simulations with that specific question in mind, the results lined up with startling precision. A massive planet sitting on an inclined distant orbit doesn't just tug on the handful of nearby objects it directly influences. Over billions of years, its gravity acts on the entire inner solar system the way a slow, sustained force acts on a spinning gyroscope, gradually walking the whole structure away from its original alignment. The simulations came back predicting a tilt of exactly 6 degrees, precisely what we observe. 2 separate anomalies, discovered independently, each one resistant to explanation entirely on its own terms, and one single, hypothetical planet capable of accounting for both at once. That kind of convergence doesn't prove anything by itself. Science is rarely that generous. But it does change the shape of the question being asked. It transforms a curiosity into a genuine pattern, and a pattern into something that quietly demands an answer. The solar system, it seemed, had been leaving marks all along, and the more closely astronomers looked, the more of those marks they found. The prediction was bold. A planet 10 times heavier than Earth, hiding in the outermost darkness of our solar system, identified entirely through mathematics rather than observation. But a prediction on paper is not a discovery. To become real, it needed to be seen. And seeing it was going to require something that reflected light simply couldn't provide. Here's the core problem with searching for Planet 9 the traditional way. Every planet ever found in our solar system was located because of light, either light it reflected back from the sun, or light it blocked as it passed in front of a distant star. That method works well enough for worlds close enough to the sun to be reasonably lit. Neptune, sitting 2.8 billion miles out, is already faint enough that it takes binoculars just to spot it. Now take something 16 times farther away than that. The amount of light a planet reflects falls off sharply with distance. Move it twice as far, and it reflects 4 times less. Move it 10 times farther, and it reflects 100 times less. At Planet 9's predicted distance, any reflected signal would be buried so deep in background noise that a traditional optical search would be like hunting in a pitch-black room with a nearly dead flashlight. So astronomers turn to a different property, one every large planet shares regardless of how far it sits from the sun. Planets are warm. Not warm the way a summer afternoon feels warm, but warm in the sense that they continuously leak energy, heat left over from their formation, from the slow settling of their own mass, from radioactive decay deep within their cores. That heat radiates outward as infrared light, invisible to human eyes but very real. Jupiter pushes out almost twice as much heat as it receives from the sun. Neptune does the same. If Planet 9 is an ice giant, as the models suggest, it should be doing exactly the same thing, quietly glowing into the surrounding darkness, even from 46 billion miles away. Detecting a signal like that requires a telescope built specifically for the task. Ordinary optical instruments are blind to it entirely. What's needed is a detector tuned to far infrared wavelengths, and critically, cooled to near absolute zero itself, because a warm telescope generates its own infrared noise that would drown out the very signal it's trying to measure. It's the astronomical equivalent of trying to hear a whisper in a quiet room while standing beside a running engine. Turn the engine off, and suddenly the whisper becomes audible. That instrument already existed. The Japanese space telescope Akari, launched in 2006, spent years mapping the entire sky in infrared, its detectors cooled with liquid helium down to just a few degrees above absolute zero. cold enough to catch thermal signals no ground-based telescope could ever measure. For years, that archive simply sat there, a complete infrared map of the sky built by a cooled space instrument, covering exactly the kind of signal Planet 9 would produce. Eventually, researchers began cross-referencing it against the predicted orbital region. The process was slow and exacting. Every point of infrared light in the target zone had to be examined individually, checked against catalogues of known stars, galaxies, and asteroids. Anything with a known identity was eliminated. The list of unexplained sources shrank candidate by candidate until something unexpected happened. It didn't shrink to zero. 2 signals remained. 2 points of infrared light with no match in any existing catalogue, sitting in the general region of sky where Planet 9's orbit was predicted to pass. What made them genuinely compelling wasn't just their existence, though. It was their behaviour over time. When the Akari data was compared against older infrared observations from a satellite launched decades earlier, both candidates appeared to have shifted positions slightly against the background stars. That kind of drift is the signature of a nearby object. Distant galaxies don't move relative to the background sky. A planet does. The temperature signatures matched what the models predicted for a large icy world at extreme distance. The positions fell within the predicted search zone. For a brief period, excitement within the planetary science community was genuine and difficult to contain. 2 candidates, both unexplained, both behaving exactly like something real. Then came the follow-up observations, and the story got complicated. When other teams turned their instruments toward the 2 candidate positions, the results refused to resolve cleanly. Some searchers couldn't confirm either signal at all. Others detected something faint at the right location, but couldn't establish whether it was moving. The one test that actually separates a solar system body from a distant background source. The data sat in an uncomfortable middle ground, not confirmed, not eliminated, not explained. Part of the difficulty traces back to Akari itself. It was a remarkable instrument for its era, but its spatial resolution had limits. A faint infrared smudge in its data could be a distant planet, or it could just as easily be an unresolved background galaxy, a known asteroid sitting outside the catalogue boundaries, or an artifact produced by the detector. Without sharper follow-up imaging from a more powerful instrument, pinning down the true nature of either candidate proved genuinely difficult. The signals were real, in the sense that something produced them. What that something actually was remained wide open. What the Akari search did establish, even without a confirmed detection, mattered for the search going forward. It proved the thermal method was viable, that far-infrared surveys could realistically find candidates in the predicted zone, and that the signal Planet 9 would produce wasn't too faint to detect in principle. It also sharpened the predicted location. Even ambiguous data narrows the map. The 2 candidates gave researchers a more specific region to focus follow-up efforts on, and a concrete scientific case for requesting time on far more powerful instruments. The most powerful of those instruments is the James Webb Space Telescope, the largest and most sensitive space observatory ever launched. Webb's infrared capabilities are extraordinary. A Planet 9-sized object within the predicted distance range would, in principle, be detectable in a reasonable observing window if the telescope were pointed at the right location. And that's the catch. Webb doesn't scan the sky. It stares at specific targets. Pointing it at a broad, undefined search zone and hoping to catch a slowly drifting infrared glow isn't a workable strategy. It requires knowing where to look with far more precision than current models alone can provide. The Akari candidates offered a starting point, not a confirmed address, but a narrowed neighbourhood. And in a search operating at the scale of billions of miles, narrowing the neighbourhood is everything. The signals had been detected. They hadn't been explained. And the next question wasn't whether Planet 9 was warm enough to find. It was whether the place those signals came from was even consistent with everything else the models predicted. That's where the story was about to take an unexpected turn, because a newly discovered object in the outer solar system was about to make the search significantly harder and significantly more interesting at the same time. Every search has a moment where the evidence stops building neatly in one direction and starts pushing back. For Planet 9, that moment arrived in the form of a single frozen object drifting quietly through the outer solar system. An object whose orbit was almost too clean, too stable, too undisturbed to fit comfortably into a solar system with a hidden giant planet nearby. The object is designated 2023 KQ-14. It belongs to a rare category of bodies called sednoids, named after Sedna, a large reddish world discovered in 2003 that puzzled astronomers from the moment they found it. Sedna's orbit never brings it close enough to Neptune for Neptune's gravity to have placed it there. It lives entirely beyond Neptune's reach, in a zone so remote that almost nothing in the standard model of solar system formation explains how an object ends up there in the first place. Finding Sedna was the first hint that something in the far outer solar system had been doing work our models hadn't accounted for. 2023 KQ-14 goes even further. Its closest approach to the Sun sits at 6.6 billion miles, more than double Neptune's orbital distance. Even at its nearest point, it drifts through a region so cold and remote that the Sun appears as nothing more than a bright star overhead. Its entire orbit from closest approach to farthest retreat unfolds in a zone of near total gravitational isolation. Neptune cannot touch it. Jupiter cannot touch it. Nothing in the known solar system has any meaningful grip on it at all. What made astronomers pay close attention wasn't just the distance, though. It was the stability. The orbit of 2023 KQ-14 is extraordinarily smooth, a clean and predictable path with no sign of recent disturbance. No wobble, no accumulated drift, no fingerprints of repeated gravitational nudging over millions of years. It moves the way an object moves when nothing massive sits nearby, constantly pushing on it. That's where the tension with Planet 9 enters. A planet 10 times heavier than Earth doesn't keep its gravitational influence neatly contained. Gravity doesn't respect boundaries. It reaches outward in every direction, weakening with distance but never fully stopping. An object drifting within a few billion miles of Planet 9 over millions of years would accumulate distortions in its orbit, small at first, but building over geological timescales into something measurable. The orbit of 2023 KQ-14 shows none of that. It looks like an object that has spent its entire existence far from anything massive enough to leave marks on it. This doesn't eliminate Planet 9 as a possibility, but it constrains it, and constrains it significantly. If the hidden planet's orbit passed close to where 2023 KQ-14 travels, that history would be written into its orbit in ways that simply aren't there, which means either Planet 9 sits farther out than early models suggested, or its orbital path curves through a different part of the outer solar system entirely, one that doesn't overlap with 2023 KQ-14's neighbourhood. The planet gets pushed deeper into the dark, the search zone shifts, the map gets redrawn. Think of it like tracking a large animal through a forest by the damage it leaves behind. Broken branches, disturbed soil, scarred bark. If you come across a stretch of forest where every tree stands untouched, you don't conclude the animal doesn't exist. You conclude it simply hasn't passed through that particular stretch of woods. 2023 KQ-14 is untouched forest. It tells researchers where Planet 9 probably isn't. And here's what makes it more than just a complication. It also contributes its own piece of supporting evidence to the larger picture. Despite its pristine orbit, the direction that orbit points in space still falls within the same general family of orientations that motivated the Planet 9 hypothesis in the first place. The clustering pattern that started this entire search includes objects like this one, Its orientation fits. It's simply telling researchers that whatever planet is responsible needs to be positioned more carefully than early models assumed. This is how science actually moves forward, not in straight lines, but through a constant dialogue between prediction and constraint. Each new object discovered in the outer solar system is another data point that either supports the model, challenges it, or reshapes it. 2023 research does the third. It accepts the broad framework while demanding more precision in the details. The existence of Planet 9 becomes harder to pin down, not harder to believe. But it isn't the only sednoid in the picture. Sedna itself has been sitting in the data since 2003, stubbornly unexplained by any model that doesn't invoke something massive in the outer solar system. Multiple stable objects now exist in this zone of supposed gravitational isolation, all moving in smooth, long-lived orbits, in a region that standard solar system formation theory says should be effectively empty. Each one required something to push it out there in the first place. Each one has stayed stable long enough to suggest that whatever did the pushing has since retreated to a comfortable distance. That pattern is itself a signature. A planet on a very long, very slow orbit would spend most of its time at the far end of that orbit, distant from the objects it influenced billions of years ago. It would shape their paths during the rare periods when it swung through their neighbourhood, then retreat back into the deep outer solar system, leaving them undisturbed for thousands of years at a stretch. The stability of the sednoids isn't evidence against Planet 9. It's evidence for a Planet 9 that moves slowly enough and stays distant enough to let the objects it once organised settle into the quiet paths we observe today. The outer solar system in this picture is not a chaotic junkyard. It's an organised place, more organised than it has any right to be, given what we know about how solar systems form and evolve. Something sorted it. Something with patience measured in billions of years and gravitational reach measured in billions of miles. And it left behind a collection of frozen worlds in stable orbits that quietly, persistently point toward a region of space where two infrared signals have already been detected and never explained. The evidence wasn't falling apart, it was becoming more specific, and in a search this difficult, more specific evidence is the closest thing to progress there is. At some point in any deep scientific mystery, the question shifts. It stops being only about whether something exists and starts becoming about what exactly that something is. For Planet 9, that shift happened gradually, and when it did, it opened a door onto possibilities that nobody had seriously considered when the search began. The default assumption, the one baked into every model and every headline since 2016, is that Planet 9 is a planet. A large, cold, icy world drifting in the dark, an ice giant like Uranus or Neptune, formed billions of years ago and flung out to the edges of the solar system by a gravitational encounter it never recovered from. That assumption is reasonable. It fits the mass estimates, and it fits what we know about how solar systems form. It's the most straightforward explanation for everything the data shows. But straightforward isn't the same as certain, and a small group of physicists decided to ask a question the planet hunters hadn't seriously entertained. What if the object pulling on the outer solar system was never a planet at all? In 2019, two researchers at Harvard published a paper that stopped a significant number of people cold. Their proposal was this: the gravitational anomalies in the outer solar system, the orbital clustering, the solar tilt, the sednoids, all of it, might be caused not by a hidden planet but by a primordial black hole. A tiny, ancient black hole formed in the first fractions of a second after the Big Bang, drifting through the galaxy for billions of years, eventually captured by our solar system's gravity, and sitting quietly in the outer darkness ever since. The mass required to produce the observed effects would be somewhere between 5 and 10 Earth masses, and a black hole carrying that much mass would be roughly the size of a grapefruit. Not a grapefruit-sized planet, a grapefruit-sized singularity, a point of such extreme density that not even light can escape from its surface, compressed into a sphere you could hold in one hand, carrying the mass of nearly 10 Earths. The reason this theory is scientifically legitimate rather than pure speculation is fairly simple. Gravity doesn't care what shape its source comes in. At long range, a 10 Earth mass black hole and a 10 Earth mass ice giant pull on surrounding objects in exactly the same way. The orbital clustering, the 6-degree solar tilt, the stable sednoids pointing toward an invisible source, all of it would look completely identical whether the cause was a planet or a black hole of equal mass. Every piece of indirect evidence gathered over the past decade is consistent with both possibilities simultaneously. The difference only becomes visible when you try to observe the object directly. A planet, however dark and cold, still has a surface. It reflects some sunlight, however faintly, and it radiates internal heat as an infrared glow. These signals are extremely faint at Planet 9's predicted distance, but they're real physical emissions that sensitive instruments can, in principle, detect. That's the entire basis of the Akari infrared search. A black hole has none of that. No surface to reflect light from, no internal structure generating heat. From an observational standpoint, it's the darkest possible object in the universe, completely invisible to every detection method the planet searchers have relied on. So how would you even find it? The most promising method involves watching for what happens when material falls toward the black hole. Even in the near vacuum of the outer solar system, small quantities of dust and gas drift through space, and occasionally some of that material would drift close enough to be captured and pulled inward. As it spirals toward the event horizon, it compresses and heats to extreme temperatures, briefly releasing a burst of high-energy radiation before crossing the point of no return. Near the centers of galaxies, this process, called accretion, produces spectacular luminosity visible across billions of light years. In the cold, nearly empty outer solar system, the same process would produce something almost imperceptibly faint. But faint isn't the same as zero. A second detection method involves gravitational lensing. When a massive object passes between Earth and a distant background star, its gravity bends the starlight around it, producing a brief brightening of that star as seen from our position. This is called microlensing, and it's a well-established technique already used to search for dark, compact objects throughout the galaxy. A primordial black hole slowly drifting through the outer solar system would produce microlensing events as it crossed in front of background stars, rare, brief, and faint, but theoretically detectable by surveys already in operation. If such an event were observed in the predicted region of sky, with no visible object found at the lensing location, a primordial black hole would become a serious candidate almost immediately. Primordial black holes themselves remain theoretical. They were proposed as objects that could have formed during the extreme density conditions of the early universe, before stars or galaxies existed, when the cosmos was still a fraction of a second old. Their existence has never been directly confirmed, and some physicists believe they could account for a portion of the universe's dark matter, the invisible mass that holds galaxies together but has never been directly detected. Others doubt they formed in meaningful numbers at all. The mathematics allows them, the observations neither confirm nor eliminate them, and the question remains genuinely open. What the Harvard paper did was force a reckoning with an uncomfortable truth. The indirect evidence for Planet 9, all of it, every piece gathered over a decade of careful work, cannot distinguish between a planet and a black hole of the same mass. The two possibilities are gravitationally identical from the outside, and the only way to tell them apart is to find the object and observe it directly. Finding something that emits no light, no heat, and no signal of any kind requires either extraordinary luck with a microlensing event or a level of precision in the search that current technology hasn't quite reached. The grapefruit in the dark. Somewhere between 18 and 46 billion miles from the Sun, something is organising the outer solar system, and it has been doing so for billions of years. It may be a frozen world the size of Neptune, quietly radiating heat into the surrounding void. It may be a relic of the Big Bang itself, a point of collapsed space-time so dense that the laws of physics as we understand them break down at its surface. Both possibilities fit the data equally well, both are extraordinary, and both are sitting in the same region of sky that two infrared signals have already pointed toward, signals that have been sitting in the data, unexplained, for years. The mystery hadn't narrowed to a single answer. It had deepened into a fork in the road, each path leading somewhere more remarkable than anyone expected when the search began. Science doesn't always move forward by finding things. Sometimes it moves forward by being forced to confront the possibility that the foundation the search is built on might not be as solid as everyone assumed. For Planet 9, that confrontation arrived not from a new discovery in the outer solar system, but from a challenge aimed directly at the mathematics that started the whole search. The case for Planet 9 rests on a pattern: 6 distant frozen objects aligned in the same direction, tilted at the same angle, clustered together in a way that seemed too precise to be random. That pattern drove the models drove the predictions, and the predictions drove a decade of searching. But a pattern is only as reliable as the data it's drawn from, and the data, it turned out, had a problem. Astronomers don't survey the sky the way a security camera covers a room, evenly and continuously, without preference. Telescopes are pointed at specific regions for specific reasons. Survey programs have scheduling constraints and sensitivity limits, and certain orbital orientations are simply more likely to be discovered than others, depending on where the surveys were conducted and what brightness thresholds the instruments were operating at. The technical term for this is observational bias, and it's one of the most persistent sources of error in astronomy. The 6 objects that launched the Planet 9 hypothesis were not found through a perfectly uniform sky survey. They were discovered in patches, during observations motivated by other science goals, using equipment with sensitivity limits that weren't uniform across the whole sky. The sample was small. The surveys that produced it weren't designed with bias avoidance as a primary goal, and in 2019, a team of researchers published a study that applied a direct statistical correction for exactly this problem. Their conclusion was stark. After accounting for the fact that certain orbital orientations are more likely to be discovered given where and how the surveys actually operated, the apparent clustering among the distant objects largely disappeared. The 6 compass needles that seemed to be pointing north were pointing north, partly because the surveys had been looking predominantly in that direction. Tilt the search toward a different part of the sky, and different objects would have been found pointing in different directions. The pattern, in this reading, wasn't a signal from a hidden planet. It was a shadow cast by incomplete surveying. If this analysis is correct, there's no anomaly to explain. The outer solar system is behaving exactly as an empty, unorganized region should, and the orbital clustering is an artifact of how humans searched, not a reflection of what the solar system actually contains. Planet 9 in this scenario was conjured from a statistical illusion, a remarkably compelling one, but an illusion nonetheless. The Planet 9 camp pushed back. Battigan and Brown argued that even with bias corrections properly applied, a statistically meaningful clustering signal survived. The pattern weakened under correction, they acknowledged, but it didn't disappear, and the residual signal they maintained still required an explanation that random chance couldn't comfortably provide. The debate that followed wasn't a polite academic disagreement, It was a genuine scientific dispute between rigorous researchers applying different methodologies to the same underlying data and arriving at meaningfully different conclusions. That dispute has not been resolved. Different teams using different bias correction methods continue to get different answers, some finding a residual clustering signal that demands explanation, others finding that the signal dissolves almost entirely once the survey's observational footprints are properly accounted for. The honest summary of where the field stands is that the statistical foundation of the Planet 9 hypothesis is contested, not debunked, not confirmed, but genuinely uncertain in ways the 2016 paper didn't fully anticipate. What this means in practice is that the entire case built on indirect evidence, the orbital clustering, the solar tilt, the sednoids, the retrograde orbiters, carries an asterisk. Each piece of evidence is real in the sense that the observations themselves are real, but whether those observations reflect a genuine pattern in the solar system or a pattern in how astronomers have explored the solar system is a question existing data cannot definitively answer. The tool used to draw the map may have introduced distortions into the map itself. This is not a failure of science. It's science working exactly as it should. A hypothesis makes predictions. Those predictions attract scrutiny. The scrutiny reveals weaknesses, and the weaknesses demand better data. The entire trajectory of the Planet 9 debate has been pushing toward one outcome: a sky survey thorough enough and unbiased enough to test the clustering pattern against a complete, evenly sampled dataset. A survey that doesn't look harder in one direction than another, that covers the whole sky with the same depth and sensitivity everywhere. That survey is now running. The Vera C. Rubin Observatory in Chile began full science operations in 2025, and its design is almost perfectly suited to resolving this specific debate. Every few nights, its enormous camera photographs the entire accessible sky, the same patches visited repeatedly, with the same instrument, under a consistent observing strategy that doesn't privilege one orbital orientation over another. When its catalogue of distant outer solar system objects grows large enough, and it will grow far larger than any previous survey, the clustering pattern will either survive the statistical test or it won't. There will be no ambiguity about the survey's coverage, and no argument about whether the bias corrections were applied correctly. The data will be as clean as ground-based astronomy can produce. If the clustering survives, if the aligned orbits remain statistically significant in a dataset built without the selection effects that haunted earlier surveys, then the case for Planet 9 becomes substantially harder to dismiss, and the skeptics will have been answered on their own terms. If the clustering dissolves, if the pattern flattens into randomness when measured against a complete and unbiased sky, then the field will face a reckoning. A decade of models, predictions, and searches will need to be reassessed from the ground up. Either outcome moves science forward. That's the thing about a well-designed test, it can't produce a useless result. A detection confirms the pattern, a non-detection clears the air, and both answers are worth having. Both answers have been a long time coming, and for the first time in the history of this search, the instrument capable of delivering one of them is already open and watching the sky. Every search eventually reaches a moment of reckoning, not the moment the answer arrives, but the moment the tools finally catch up to the question. For Planet 9, that moment isn't approaching, it's here. The decade of indirect evidence, contested statistics, infrared candidates, and competing theories has been building toward a single instrument, a single survey, and a window of time short enough that the people who started this search may actually live to see how it ends. The Vera C. Rubin Observatory sits in the mountains of northern Chile, at an elevation of roughly 8,800 feet. From that altitude, above a significant fraction of the atmosphere's distorting moisture, its view of the southern sky is extraordinary. The telescope itself isn't the largest ever built. There are mirrors in existence that dwarf it. What makes Rubin singular is its camera, the largest digital astronomical camera ever constructed, capturing images with a resolution so high that a single frame would fill thousands of standard computer screens. It collects light efficiently enough to detect objects 100 times fainter than anything visible to the naked eye under perfect conditions, and it does this not by staring at one target for hundreds of hours, but by moving, covering the entire accessible sky every few nights, building a database of every point of light visible from that mountaintop, returning to the same patches of sky again and again across a 10-year program called the Legacy Survey of Space and Time. This is exactly what the Planet 9 search has needed since the beginning. Not more power aimed at a single predicted location, but systematic, unbiased coverage of the whole sky. The same depth everywhere, the same sensitivity everywhere, the same revisit cadence everywhere. Every image compared automatically against the last, every point of light that has shifted position between visits flagged for follow-up. The selection bias that undermined earlier surveys, the problem of looking harder in some directions than others, is structurally eliminated by a telescope that doesn't play favourites with the sky. The predictions from the planetary science community are specific. If Planet 9 exists anywhere within its estimated orbital range and isn't currently positioned directly behind the densest star fields of the Milky Way, the Rubin survey should find it within its 10-year run. Some estimates are more optimistic than that. If the planet happens to be sitting in a region of sky already covered in the survey's early observations, a detection could come within the first 2 or 3 years. The survey began full science operations in 2025, and the clock is already running. What a confirmed detection would mean is difficult to fully absorb. A 9th planet, a super-Earth sitting in our own solar system, undetected through the entire history of human astronomy, found at last by a camera in the Chilean mountains photographing the sky on a quiet Tuesday night. The announcement would be the largest in planetary science in a generation, larger in its implications than the discovery of any exoplanet, because this one is ours. It belongs to the same solar system as Earth. It formed from the same cloud of gas and dust, and it has been here the entire time. The immediate scientific response would be total reorganization. Every observatory with relevant capabilities would redirect resources toward the confirmed location, and the James Webb Space Telescope would be pointed at it within weeks, building the first detailed infrared portrait of a world that has existed in complete darkness and complete anonymity for 4.5 billion years. Ground-based telescopes across both hemispheres would begin the long process of precisely mapping its orbit, measuring its size, and studying its atmospheric composition from the faint spectral fingerprints its light carries across billions of miles. A new chapter of solar system science would open overnight. The discovery would also force a fundamental rewrite of how we understand solar system formation. The current models describe a solar system built from 4 rocky inner planets and 4 outer giants, arranged through a specific sequence of gravitational interactions and migrations. Planet 9 doesn't fit that picture. It's a 5th giant, one the models didn't predict and don't currently accommodate. Its existence would mean the early solar system was more chaotic, more populated, and more violent than any textbook currently describes, and the Nice model, which explains the current arrangement of the giant planets, would need to be rebuilt from scratch around a 5th player that was eventually thrown out of the game, and then there's what its discovery would mean for our understanding of other solar systems. The most common type of planet found around other stars is a super-Earth, a world with a mass between Earth and Neptune, absent from our own solar system in a way that has puzzled astronomers for years. Planet 9, if confirmed, would be our super-Earth, the planet that should occupy that gap in our lineup, sitting not in a comfortable orbit close to the Sun but exiled to the outermost darkness by a gravitational encounter it never recovered from. Our solar system wouldn't be unusual for lacking a super-Earth. It would be unusual for having lost one so completely that it took humanity until the 21st century to find the evidence it left behind. But the Rubin Observatory survey carries a second possible outcome, equally significant and considerably more unsettling. If the full 10-year program completes its coverage of the predicted search zone and returns nothing, no slowly drifting infrared smudge, no faint moving object in the right orbital range, no candidate that survives follow-up, that silence will be its own kind of answer. It will mean the orbital anomalies that launched this entire search aren't caused by a hidden planet, and the clustering, the solar tilt, the sednoids, the retrograde orbiters, all of it real, all of it unexplained, and none of it attributable to a ninth planet. Something else is responsible. That something else could be the distributed mass of millions of undetected small bodies in the outer solar system, their combined gravity mimicking the effect of a single large planet. It could be a primordial black hole, invisible to every detection method the survey employs, identifiable only through the rare gravitational lensing events that dedicated searches would need decades to catch. Or it could be something more fundamental, a signal that the laws of gravity themselves behave differently at the extreme distances and vanishingly weak accelerations of the far outer solar system, a gap in physics that no additional planet, however large or however distant, could fill. Two infrared signals sit in an archive unexplained. Dozens of frozen worlds point toward the same empty region of sky, and the solar system lists 6 degrees from where it should be sitting. Something out there has been leaving marks for 4 billion years, and the Rubin Observatory is photographing that region of sky right now, tonight, building the dataset that will finally force an answer. Whether that answer is a hidden world or a hole in our understanding of reality itself, it is coming. The signals are real, the search is almost over, and whatever is waiting at the end of it has been patient long enough. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.